Here's where we left off, and we were talking about Grubbs from Possum Trot, Kentucky, basically targeting a double bond and cleaving that double bond and making these fragments that we glue back together and call them products. And that's really all that metathesis basically is. But I left you with this idea, and here's the idea. What if we had a ring that's delocalized, and the top piece maybe here, and the bottom piece, 1, 2, 3, maybe there. And we add Grubbs to this. What happens? Oh, okay, you just told me what metathesis did. You just told me what Grubbs did. So I'll take a look at this double bond, and I will that piece, and then I'll that piece, right? And we get these fragments, and this fragment is a double bond carbon. There's just one of them on that side. Another double bond carbon. There's one on that side. And then I get this ring structure that's still held together. That's something that looks like this, and then something that looks like this, that needs pieces as well. So if these two pieces come together, matchmaker, matchmaker, it ends up with the same thing. These two pieces come together, matchmaker, matchmaker, it ends up with the same thing. I'm not going to waste my time to draw it. If the two pieces on the right come together, ding ding, there's our first product, and there's my C double bond C. Ethene has been formed. But there is another product that can happen here. I know that this molecule to the left-hand side weirds you out a little bit. Weirds me out too. All right. But the way that I want you to think of this is a carbon that partially has a double bond, and a carbon here that partially has a double bond. And they're looking for the other half. They are on a journey of life, and they are looking for their magic other half that just completes them. Well, some of you have been lucky, and you have found that other half in your life. And these carbons are getting ready to find it in theirs. It's a little love story. So the carbon on the top and the carbon on the bottom look at each other and say, hey, I have half of what you need and you have half of what I need. So why don't we just come together and make our two halves as one? And we both will be satisfied, and this makes our molecule perfectly happy. And that is another choice that begins to happen as far as my product goes. So we can take these open chains, and these open chains can come together. Look, especially if they're held together here, right? They can't separate too far. And it just so happens that it makes a 6-membered ring. And this 6-membered ring, as we talked about in Orgo 1, was very stabilizing to a ring structure, right? 3-membered rings, there's too much strain. 4-membered rings, too much strain. 5-membered rings would get a little bit better. 6-membered rings, oh yeah, that's the Goldilocks moment. Then we go to 7 and 8 and 9, and the rings just get too floppy. They can't really hold up anything. So 6-membered rings are great. The molecule knew that a 6-membered ring could form here. Those two carbons were side by side. They were neighbors that fell madly in love with each other. So how easy would this going to be? And we get this product that forms because of that. Now, mechanism. I told you mechanism is going to be a thing that we're not going to worry with. But folks, here's kind of the first step of the mechanism, because I do have those people that are like, I wonder what the mechanism would look like. Okay, well, if that's one of you, then that's fine. I'm not saying that you shouldn't. But if you are a little bit more inquisitive on how this process happens, here you go. And you're going to see why I'm not going to ask you to memorize this mechanism. Once more, mechanism kind of understood, but not fully. We don't really want to set anything in stone at this point. But it looks like the Grubbs catalyst is going to be right here, and that M, of course, is going to represent the ruthenium. And the most important piece is that double bond with this carbon and the benzyl ring. All right, so here is that metal catalyst. That metal catalyst comes and sits down on top of that alkene. And this metal kind of grabs one of those carbons and it grabs the other one of those carbons and it makes this cyclic intermediate in a way. And then the metal is going to decide to, there we go, and we get a half of a molecule with a metal on it, and the other half of the molecule does not have one. Well, the process can repeat, and the metal can decide to a different way. And when it does that, we now have another half of the molecule with a metal and another half that's a little bit different. All right, so that's the first half of the mechanism. The second half of the mechanism is that these pieces will begin to join together, and this is how we get these new alkenes that form because of that. So these are cycloadditions. You can see why they're called a cycloaddition, because we are making cyclic intermediates, and these metals are breaking bonds kind of at the same time and making just different decisions based on however they feel at that moment in time. All right, so let's take a look at an example. Here's an example. And in this example, it's basically going to say, here's choice A, B, C, and D. So if these molecules undergo metathesis, what types of products would be formed? Okay, well, no big deal. This is something that we've done already. They're just putting it into a little bit more formal presentation for us. So let's show metathesis who's the boss. Here we're going to take CH3, CH2, CH, and there's half of that bond, and then here's half of that one. We kind of done something similar to this already, but we'll do it again. Practice makes perfect, even though I'm not asking you to be perfect. All right, so here are basically two molecules of the same. That's how the question's worded. Suppose you have 2 moles of each of the following molecules. What would be the products of the metathesis reaction? Okay, so here's the halves. So if this half meets up with that half, it gives me the reagent that I started with, right? So the only way that we're going to get something different is if these two halves come together. So CH3, CH2, CH double bond, CH, CH2, CH3. And then if these halves come together. So this gives me a CH2, double bond, and CH2. All right, so there we go. Now let's take a look at B. B is going to be a little different. 2 moles of that one, 2 molecules of that one. So here, 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 and there's half of that double bond, and then there's a stick. And then the other half of this double bond would be a carbon, just 1 carbon with a double bond that's there. All right, so if I've got 2 molecules of this thing, I'm going to see this again, and then once more, here, 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 double bond, and then there we go. So I'm going to have to group these 2 things together, and this gives me a CH2 double bond CH2. And then I'm going to have to group these 2 things together. Whew. Okay, so let's do that over here to the right-hand side. This looks kind of nasty, doesn't it? All right, well, let's look at my longest carbon chain first. That would be the easiest. 1, 2, 3, 4, 5, 6. Then it wraps up to right there. So 7, 8, 9, 10, and 11. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. 1, 2, 3 from the end, I get a carbon that goes down. 1, 2, 3 from the end, I get a carbon that goes down. Same thing's going to happen over here. 1, 2, 3, 4, 5, 6. There's the connector piece. 7, 8, 9. I'm going to see a carbon that goes down. Or, in other words, 3 from that end. All right, so 1, 2, 3 from that end. There we go. And where's that double bond? 1, 2, 3, 4, 5. On that 5th carbon, that is where this double bond is going to be located. All right, so 1, 2, 3, 4, 5. And that's where my double bond is going to be. There you go, folks. That's all there is to it. I also want to talk a little bit about stereochemistry before we go on. As far as the stereochemistry goes, the CH2 groups, there's no stereochemistry here. There's 2 hydrogens on the left and 2 hydrogens on the right. I can't really compare them. I can't really rank them. So stereochemistry does not get involved in that discussion. The same thing's going to happen down here. Stereochemistry is not going to happen in that discussion. All right, if I look at this product choice though, right, here's my carbon double bond carbon. So I'm going to draw it this way. And then this carbon on the left has an ethyl group and a hydrogen on it. All right, so here is the ethyl and here's the hydrogen. And then the carbon on the right also has the same thing. We have a hydrogen and an ethyl group. So you're probably going to say to me, well, I think the trans would probably be formed more, right? We have this trans orientation around that double bond? And the answer is yes, trans does get formed. However, cis also has the chance to get formed if it can. It's going to. So this is not stereo specific. This is going to just basically glue the pieces together. It doesn't really matter how they glue them together. And we're going to get both a mix of cis and trans that's going to be formed in this particular type of molecule. All right. The same thing's going to happen up here. So this double bond, I do have cis and I do have trans that can form about that double bond. And both of those are going to happen. All right. Now let's take a look at C. I'm going to do this on a different screen. All right. So for C, they're going to tell me I've got this CH2 group and then this double bond carbon with a CH3 here and a CH3 there. All right, so 2 molecules of it. So it's going to metathesize with itself. All right, so I'm going to take my eraser and there we go. And there's my 2 fragment pieces. All right, so one of these fragment pieces I can join will be these 2 together to give me CH2 double bond CH2. So 2 halves make a whole. And then the other part will be over here. So this carbon that has a methyl group pointed up and a methyl group that's pointed down, double bond or a fraction of a double bond, will hook up with that carbon that also has fractions. So 2 halves make a whole. And that carbon also has a CH3 up and a CH3 down. So this one, there's no stereochemistry. The reason is that there's 2 hydrogens on the left and there's 2 hydrogens on the right. I can't rank them. And then this molecule over on the right-hand side, no stereochemistry there either. And the reason is that this is a methyl group and that's a methyl group. I can't rank them. They're the same. And this is a methyl and that's a methyl. I can't rank those. They're the same. So because I can't rank them, I cannot assign a cis or a trans to that double bonded molecule. All right? So there's C. Now let's take a look at D. D is going to give me a 6-membered ring like this, and then a double bond that goes out to a CH2 group. All right, well, I know that they're going to tell me 2 moles. All right, so I'm going to draw 2 of them. So I'm going to take my eraser. That's why they give you erasers on pencils. Bring a pencil, right? Do the homework in pencil. Not a big deal. Nobody's going to scream. That's why it's made. That's why it's for. That's what it's for. There we go. All right, so there's the 2 fragment pieces, and now we need to glue them together. All right, to glue these together, well, here's the first half, CH2 double bond CH2. Seems like we get that a lot, don't we? And then over here on the left-hand side, I've got this 6-membered ring structure that has a double bond that goes out. And that's going to hook up with this half down here. That's going to also be a carbon in a 6-membered ring structure. So there we go. 2 6-membered rings that are connected by a double bond. Let's look at another example. The following form rings when they undergo metathesis. What would those rings be? Well, at least they tell me they're going to form rings. At least they give me that much information. Let's look at A. How do we do this? There's our cleaves. So it looks like when I do this, this carbon, double bond, this carbon, double bond. So we get that traditional ethene that we've seen in all the other example problems. How many carbons do I have left? Well, I've got 1, 2, 3, 4, 5, 6. Oh my goodness, look at there. A 6-membered ring can come together and form a double bond, right? And that double bond can form right there. So this carbon, I'm going to color in red. That could be this one, right? And then this carbon over here at the very end also has half of a double bond that it needs satisfied. It just so happens to be at the end of that chain, and the end of that chain can circle and snake around, and that would be that carbon. So those two carbons have came together on the ends in order to form a double bond. Notice this takes a diene in order for that to happen. We had a double bond here. There's one ene, and we have a double bond there. There's two enes, which we call diene. So circle around, not a problem. The two carbons can link up, and there we go. Let's take a look at B. There we go. So this carbon has a double bond. That carbon has a double bond. Those two things come together and form ethene, just like the others. Now what? Okay, well, it looks like we have a carbon that's here. 1, 2, 3, 4, 5. So that could circle back around because the half of that double bond and the half of that double bond needs to be satisfied. These two carbons can't get away from each other, and if they just kind of circle that double bond around, they can hook back up and they can satisfy each other's needs. They're neighbors, again, falling madly in love, and they're getting ready to have a product baby. All right, so here is my 6-membered ring. And then off of this, we now know there's a 5-membered ring. So 1, 2. So there's that one, 1 and 2. This one is the third one that has the methyl group that's pointed off. And that has the double bond. So half of that double bond is going to come from that carbon. Down here, I have an OCH3. I can't forget about that, right? We didn't do anything with it, but it's still there. So there's OCH3. Then that goes to a carbon. That would be here. And then that goes to a carbon that also has half of a double bond. And it just so happens it's right beside of one that also had a half. So that's where my double bond would form. Right there between those two carbons, and that's where they need them. Now let's take a look at C. Again, what do you think I'm going to do? There we go. So this carbon and this carbon come together right now. All right, so there's my carbon, double bond carbon. There's my ethene, just like all the other times. This nitrogen-containing group still has that methyl group that's hanging off of it. This nitrogen also has this carbon, and this carbon has a partial double bond. All right, so I know that a double bond is going to form kind of right there. I've got to figure out how many carbons are going to be in this ring, though, because that's what the question says. It's going to form a ring, so they're at least letting me know that. All right, so here's the nitrogen. To the left-hand side of it, I've got 1, 2, 3, 4, and 5. So I'm going to have to do 1, 2, 3, 4, and 5. And that is what's going to finish up that double bond. It's going to be right there. All right. So this is a kind of floppy little ring. It's not a 6-membered ring. It's okay. It's not as stable as a 6-membered ring, but they can still form, folks. I mean, this is going to be perfectly okay if that's what we do. Let's look at another type of example. How to make these. How would you make the following molecules if they underwent a metathesis reaction? What reagents would be needed? Okay, so the way we solve this problem, There's A, there's my double bond. There we go. So we open up that ring system. All right, so this ring system looks like there was a carbon right there. That's where I'm going to start. That carbon had a double bond on it, and that eventually went to a carbon right there. So I've got another carbon there, and then another one here, another one there, another one here. And folks, it looks like that was a double bond to another carbon. There we go. That's what was done. Because what would happen here is and then and one of those products would be a carbon double bond carbon that would represent the carbon here and the carbon there. And the other, well, the carbons would wrap around on themselves. It's a diene. And this is a 1, 2, 3, 4, 5-membered ring that has a double bond. And that's exactly what we have in part A. So there we go. That's what we could use. For part B, how would we make that one? Okay, pretty simple here. There's where the double bond's at. Okay, so let's talk about how that double bond could have been formed. That double bond was there. And I'll draw the rest of the molecule because it was probably onto another carbon. Okay, if that was the case, then we would that out, and I would get carbon double bond carbon, and then I would get this other carbon fragment that would come together with another molecule of this carbon fragment, and it would give me B as one of the possibilities of the products that metathesis would create. All right, let's look at another. How do you make these? Oh, these look like they're getting harder. No, they're not. They're not getting any harder. There you go. That's all that you need. So let me redraw this, and I'll show you how I like to solve these problems, just to kind of keep my head on straight. If you think that I have my head on straight, that's a different story. All right, 6-membered ring, 5-membered ring. There we go. All right, well, this is the double bond. I'm not going to destroy the delocalized system. That molecule likes that too much. It's not going to tamper with that at all. It's delocalized, double single, all the way around. So the double bond here that I need to, this is going to be right there. So when I break that double bond, this carbon would have a double bond that leads to another carbon, right? So I'm going to get rid of that. And then this carbon down here below, that also has a double bond that would eventually lead to another carbon as well. So that way, when the metathesis comes around, it's going to cleave this double bond, cleave that double bond, a carbon double bond carbon gets spit out as a product, and this carbon has a half, this carbon has a half, and what we would see is a double bond that forms right there between the two. So that would be the proper reagent or the starting material in order to make that product that they showed me on the screen. All right, so that's kind of the trick that I like to do. Again, eraser is your friend. Okay, so now let's take a look at this other one. There's an oxygen, a double bonds here, and then we get an ethyl group that points off right there. All right, so pretty crappy looking ring, but that's what that is. Once again, what product would, or what reagent would be needed to make this ring? Okay, so I'm going to... That's the only double bond I can choose from, right? So this particular carbon right there has a double bond probably to another carbon before the metathesis takes place. And then the same thing happens here. There's a carbon that has a double bond before the metathesis takes place. So there's the way that we can draw that reagent. And if this undergoes metathesis, I'm going to see a bond and a bond, and this carbon and that carbon can come together to make ethene, just like it always has, really. And then this carbon has half of a double, this carbon has half of a double, and those two halves can come together to make our double bond right there. And that's exactly the product that we needed. All right, so the starting reagent that I would need to make part B would be this one right there. All right, so there's A and there's B. That's solved for you. Woo! Not yet done. Because I want you to know that we can also do this with triple bonds. I'm not going to go through any examples too much. We'll do one. But the idea is really the same. I have triple bonds instead of double bonds, but it requires a different type of catalyst. It's not really called the Grubbs catalyst. It's called the Schrock catalyst. And the Schrock catalyst uses a different type of metal. And the Schrock catalyst targets the triple bonds and all the way down the triples. And it glues the triples together just like it glues the doubles together. There's no difference here. I mean, our reasoning, the way that we kind of come up with our products are going to be the same way. It's just a different type of metal is needed for a triple bonded carbon system rather than a double bonded carbon system. So it's not called a Grubbs. It's going to be called a Schrock. All right, so here's an example, and it says, how do you make this? All right, well, how do we make it? I see a triple bond that's here. So I know that we're going to have to Schrock it, not Grubbs it. And I'm going to all the way down. That's how we do it. So over here to the left-hand side, I have a ring system. That carbon has a triple bond, probably to another carbon. And then on this side, I'm going to see a ring system with a methyl group, and that has a carbon that's a triple bond, and that was probably to a carbon as well. So that way when I add the Schrock, I'm going to see the bond and the bond. These two pieces will come together to make ethine or acetylene gas, and this joining fragment will join up with that fragment, and a coupling reaction, matchmaker happens, and we get those two pieces that get joined together. Very similar to the Grubbs, almost identical. It just a different metal's needed for the triple bonds than it is for the doubles. So that's why I only do one of these examples, because folks, it's pretty much the same thing. Finally, the very last thing that I want to talk about in organometallic is just kind of a highlight of an example problem that we did in an earlier video, and that was the Stille reaction. So the Stille reaction is basically an organometallic that used tin. And we saw this in the palladium coupling, and this was just another way to group these two carbons together. So what you're seeing in the Stille reaction, they're using tin as the metal. And this bromo group is leaving, and this alkyl group is going on in its place. So there is no difference as far as, you know, the things that we were talking about during that time were the Heck and the Suzuki reactions. Those were our palladium-based reactions. This is just a different organometallic that uses tin. Quite honestly, I don't even know if they talk about it in your textbook, but I think it's at least worth mentioning. We also, remember, OTFs are just like the halogens. So these groups can leave, and this tin group can bring on an alkyl group, and that alkyl group can replace that halogen just like before. Again, similar to Suzuki, similar to the Heck, we're joining two of the carbons together to make longer carbon chains, and tin is another metal that will allow that to happen. So this is coupling tin and palladium both, though, because I still see palladium in this, right? And I still see palladium in that. So one of those examples kind of went off on a tangent, and it said, well, imagine that this is what you did, and you put tin in it, and it basically underwent the same type of reaction. What would be the product? So this is kind of a more detailed approach, if you want to even look at it as details, with the Stille reaction. All right, so with that said, I'm done. I am done with organic. You are done with organometallics. We do not have to talk about organometallics anymore. And folks, this wraps up the lecture material. Lithium-based, magnesium-based, Grignards, copper lithium-based, couples. That was our first coupling, Gilman's. Suzuki's that included borons and palladiums, the Heck reactions that were palladiums and just simple old alkenes. We then moved on. We talked about this Stille reaction now that was very much like Suzuki and Heck. It just used a little bit of tin. And then we talked about Grubbs, and that was a ruthenium based. So folks, there's a very small assortment of organometallics, and this field is continuing to grow. We're doing more and more research with the metal chemistries, the organometallics. There's still a lot to learn with them, but you can kind of see the power of organometallics at this point. These are reactions that will elongate the carbon chains, and the reason is because these carbons that they generate are typically negative based. So they become negative or nucleophiles in a reaction, and that allows us to group and connect these pieces together. So, you are finished with organometallics. Go celebrate. Go do the homeworks. Do those online assignments. Show me how easy this material actually is. And I think that you'll be very pleased with what you see. Once again, it's all about learning. And I think that if you look at now to where you started with, I hope that you've learned something about organometallics. If so, you are doing your job the proper way. Just keep doing it for the rest of the semester, and you'll be perfectly fine. All right, so that's where I'm stopping this video. That's where I'm stopping this lecture material. Good luck. And if you have questions, you know how to get in contact with me. I'm not a stranger. Shoot me an email. Shoot me a text. Stop by the office. Until then, I'll see you in the next lecture.